In this chapter, we'll learn about the Laplace transform and how to use the Laplace transform in solving initial value problems. And this lecture discusses the definition of the Laplace transform. And we will see a few examples how to compute the Laplace transform. And in later lecture, we'll learn how to use Laplace transform to solve differential equations. So essentially, we think of Laplace transform as a machine or a black box. So the Laplace transform takes an input, which is a function, say f of the variable for us will be x. It takes a function like this as an input, you go through the Laplace transform, and we have an output, which is a new function denoted by a script L for Laplace of f. But it has a new variable, and usually we use variable s. The new function here can also be denoted by capital F. So keep in mind that we have a function f going in as an input, and for output we have a different function with a different variable. So the definition of the Laplace transform would give us a formula which tells us how to compute the new function in terms of the given one. Let fx be a function defined for x bigger than or equal to 0. Then the Laplace transform of f is given by this formula. Script f as a script L of f or some f of x given by an integral. And this is the an improper integral that you learned in calculus 2. Integral from 0 to infinity of f of x e to the minus s times x dx. As in calculus 2, the improper integral from 0 to infinity actually means that the limit of the integral from 0 to capital A of f of x e to the minus s times x dx, and we take limit when a goes to infinity. The integral from 0 to a can be computed exactly the same way as you would do for calculus 1 or calculus 2, and we may need to use certain methods of integration like substitution, integration by parts, etc. So know that in the integration we integrate with respect to x, and s is the parameter. S is the new variable that we will have at the end. That's the variable for the Laplace transform. However, in general, the integral here or the limit here may not exist for all s. It's only true for those values of s for which the limit exists. So we will see examples which uses the definition later. So from the definition, it turns out that not all functions have Laplace transform. Only certain type of functions can have Laplace transform. And because of that, we need the following definitions called exponentially bounded function. Exponentially bounded functions. These functions are function of x, f(x), for which we can find two positive numbers. M and alpha, such that absolute value of f of x less than or equals to m times e to the alpha x for all x greater than or equal to 0. So exponentially bounded functions exactly means that the function can be bounded by a constant times an exponential function. What we want is that the function should not grow too fast. It could grow exponentially, but not faster than that. This is just a technical condition, kind of like theoretical condition. For us in practice, most or actually all of our functions would be exponentially bounded, so we wouldn't care much to check that the function will have satisfied this condition. But here's the fact that for such an f as above, the Laplace transform L of f(x). Again, the Laplace transform is a new function in the variable s. So for such a function, the Laplace transform is defined for all s bigger than alpha. Provided that s is bigger than alpha, the Laplace transform is defined. So let's compute a few Laplace transform using the definition. So consider our constant function f of x equal to 1 for all x. This is a constant function 1. So we want to know what is the Laplace transform of this function, which is just what is Laplace transform of that. By the definition of the Laplace transform, is the integral from 0 to infinity of the function, which is 1 times e to the minus s times x dx. And well, we have limit a go to infinity, integral from 0 to a of e to the minus s times x dx. For the integral here, we can use antiderivative. Keeping in mind, we always have the limit in front. An antiderivative of e to the minus s times x. The variable is x. So we get e to the minus s times x divided by minus s. We evaluate x go from 0 to a. Here we're assuming that s is different from 0, so we could find antiderivative like this. And plug in x equal to a, we have e to the minus s times a over minus s minus x equals 0. When x equals 0, e to the minus s 0 here. This, of course, becomes 1. So essentially, we have limit a goes to infinity of e to the minus s times a over minus s. And here minus, two minus side becomes plus 1 over s. Now we need to compute the limit here. When a goes to infinity. So look at this limit. We have minus e to the minus s times a. When a goes to infinity, we get e to the minus sa. So provided that s is positive, then s times a would be positive, and because a goes to infinity, s times a would go to infinity as well. But there's a minus sign in front of the exponent. Then the entire expression would go to 0. So it's better to rewrite this way. Limit of 1 over, you see, minus s, and then e to the s times a. A go to infinity, we have 1 over s. So if s is positive, then e to the sa would go to positive infinity, so the reciprocal would go to 0. On the other hand, if s is negative, the limit would go to infinity. We don't want that. And when we talk about Laplace transform, we only consider those values of s for which the limit exists. So for this problem, we only consider s positive. And as I said, the limit would be 0. So with 0 plus, we have 1 over s. This is provided that s is positive. And the reason is because limit of e to the minus s times a when a goes to infinity equals 0 if s is positive. That's what we need. And remember that the 1 plus s is the second term in the limit, which does not have a in it. So what we have computed is that the Laplace transform of constant 1 is just 1 over s, but we need to assume that s is positive. That's the first formula for the Laplace transform. Now let us look at another example. Find the Laplace transform of, say, e to the 3x. We begin by writing down the definition. Laplace transform of e to the 3x is the integral from 0 to infinity of e to the 3x times e to the minus sx dx. As before, this is the limit. A goes to infinity, integral from 0 to a. And we should combine the two exponential as well. We get e to the 3x minus sx dx. So we get limit a go to infinity, integral from 0 to a of e to the, I will factor the common factor x out, and I have 3 minus s of x dx. As before, we compute antiderivative. The variable of integration is x, so antiderivative of e to the 3 minus s times x will be the same exponential, e to the 3 minus s times x divided by the constant in front of x, so 3 minus s here. X go from 0 to a. We plug the values in. We have e to the 3 minus s times a over 3 minus s, then minus, plug x with 0 in, we have e to 0. As before, we get 1 over 3 minus s. Now we need to take the limit of the first fraction when a goes to infinity. And we want the limit to exist. So as before, if the coefficient in front of a, 3 minus s here, is negative, then the limit would be 0. Otherwise, the limit would be infinity. So we want that to be positive. We want the coefficient in front of a to be negative. So 3 minus s is negative. Let me just write down. If the coefficient 3 minus s is negative, then a limit of e to the 3 minus s times a over 3 minus s here, a go to infinity would be 0. And hence, the Laplace transform of e to 3x can be computed using the formula here. The limit would be 0, so we only have minus 1 over 3 minus s. And normally we would just distribute the minus sign in the denominator to get a better looking formula, 1 over s minus 3. So the formula is Laplace transform of e to 3x equal to 1 over s minus 3, but we need to have a condition on s, provided that 3 minus s is negative, which is equivalent to saying that s is bigger than 3. So you see that from the first two examples, we use a definition to compute the Laplace transform, and always we should have the condition on the independent variable s for the Laplace transform. Always we should have that. Now next we look at another example. In this case, we have a piecewise defined function, a function with two different formula. Define f of x is like this, equal to 0 for x between 0 and 5, and then x for x bigger than equal to 5. Find the Laplace transform of f. Now note that the function has two different formula, 0 and different intervals of x. For x between 0 and 5, the function is just 0. But for x between 5 and infinity, the formula is x. So to see what is going on, probably is a good idea to sketch the graph of this function. You should try yourself here. Between 0 and 5, the function is 0. So the graph is horizontal line out here. 0 is included, so we have a solid circle, and 5 is not included in the first formula. And then when x equal to 5, the function is actually equal, fx equal to x, which is 5. So there is a jump to have a new piece right here, a solid. And say when x equal to 6, the function would be 6x as well. So we have a straight line. And let's keep going. So this is a piecewise defined function with two pieces for the graph. So how do we compute the Laplace transform? Now, even though we have two different formulas, they are in the different intervals, so you cannot separate them into like Laplace transform of 0 and Laplace transform of x. That is not correct. 0 is only valid when x between 0 and 5, and x is only valid when x between infinity 5 and infinity. But in any case, we can compute the Laplace transform by first writing down the integral from 0 to infinity of f of x e to the minus s times x dx. And now we can look at the function, the formula for the function. Between 0 and 5, f has a different formula, and between 5 and infinity, f has a different formula. So because of that, it may be a good idea to split the Laplace transform, the integral for the Laplace transform, into two pieces, integral from 0 to 5. On this interval, the function has a different formula. And then from 5 to infinity, and on this interval, the function fx has a different formula as well. And And for each interval, we plug the formula in. If the function has three formulas, you would split into three integrals. Now for the first one, between 0 and 5, the function is 0. So I just have 0 to 5, function is 0, e to the minus s times x dx. But of course, 0 times anything is 0, so the integral here would be 0. For the second piece, the function is x. So I replace fx by x, and I have x times e to the minus s times x dx. And now I take the limit a goes to infinity, integral from 5 to a of x e to the minus sx dx. We need to use integration by parts. Or you may use tabular integrations if you prefer. Let me recall integration by parts with limit as integral from say a to b of u dv is u times v from a to b minus integral from a to b of v du. For this problem, we're gonna use u as x and dv as exponential e to the minus s times x dx. I'm not gonna go into the details. Instead, I'm gonna just write down the integral. We would have x e to the minus s times x divided by minus s. This is from 5 to a minus integral from 5 to a of e to the minus s times x over minus s dx. Now, I use 5 because the integral begins at 5 here, 5 to a. It's not from 0 anymore. For the second formula, fx equal to x, we need to use from 5. And of course, the limit here is for entire integral. Let me write one more line with antiderivative. I plug in x equal to a, so a e to the minus s times a over minus s minus x equal to 5, so 5 e to the minus s times 5 over minus s. And for the antiderivative, I would have antiderivative e to the minus s times x. I have another factor of minus s in the denominator. It turns out we have this e to the minus s times x divided by s squared. X from 5 to a. Again, I would recommend that you use integration by parts yourself to see what's going on here. Keeping in mind that s is considered to be a constant during the calculation. The integral is in terms of x only. So we have limit a go to infinity of this. Simplify the expression a little bit. 2 minus signs become plus 5e to the minus, and I usually write the constant in front, the coefficient in front, so e to the minus 5s s here, minus, plug in a, we have e to the minus s times a by s squared, plug in 5, we have e to the minus 5s over s squared. When we taking when we're taking limit here, some terms depend on a, but some terms do not have a. Let's group, let's put those terms with a into one group. The first group, say a here, e to the minus s times a over minus s, and then I have minus e to the minus s times a over s squared, and the rest is 5 e to the minus 5s over s plus e to the minus 5s over s squared. We want to see which values of s make the limit exist. As we saw earlier, we have here the factor of minus sa in the exponent. So if s is positive, this limit will be 0. That's good. Now for the first limit, we have two things. E to the minus sa, but also a in the numerator right here. So what do we do? When a goes to infinity, we would have infinity times 0. In that case, we should use L'Hopital's rule. Let me rewrite one more time. A goes to infinity, and then we have minus 1 over s, so minus s in the denominator already. And we have here, I rewrite, I'm rewriting, we have minus s in the denominator already, and then I'm rewriting this as a fraction. So a divided by e to the sa. And then here, we did that earlier, so we don't need to rewrite it, e to the minus sa over s squared, I believe. Now plus 5 e to the minus 5s over s plus e to the minus 5s over s squared. If s is positive, then if s is positive, then we saw earlier limit of the second terms minus e to the minus s times a over s squared here. When a goes to infinity, it would be 0 because the exponent goes to minus infinity. But also, for the limit minus 1 over s here, a over e to the s times a, this is of the form infinity over infinity. And if we use L'Hopital's rule, we need to take the derivative in a. The derivative of the numerator in a is 1. The derivative of the denominator in a will give us e to the s times a, and then by the chain rule we have a factor of s here. So then still we have 1 divided by the denominator goes to infinity. so still 0. So even though we have infinity over infinity, the final limit is still 0, provided that s is positive. Because the limit of the first two terms is 0, the Laplace transform is just the last two terms. So we have the conclusion. So the Laplace transform of our function f of x is 5e to the minus 5s over s plus e to the minus 5s over s squared, provided that s is positive. So you see above that we have used some limit formulas, and those limits are 0. Let me just list here a few limits that you may use. I would say common limits that needed for Laplace transform is that the limit of e to the minus s times a go to infinity. Let's see, instead of s, let me use something more general. Let's say c here, because sometimes the coefficient in front of a may not be exactly s, but it's related with s. And this limit will be 0, provided that c is positive. And also, if we have a times e to the minus c times a, then we have the form infinity times 0. But after using L'Hopital's rule like we did in the example, limit also is 0. Again, provided that c is positive. Let me write another one, that if we have a squared and e to the minus c times a go to infinity, then still the limit would be 0, provided that c is positive. These are the common limits that we will need to use in computing Laplace transform. Now, I would like to conclude this lecture by writing down a few properties of the Laplace transform that we will need to use later on. Properties of Laplace transform. The first property is called the linearity. Essentially, what it says is that if we have Laplace transform of a sum, Laplace transform of fx plus gx, then we can split into Laplace transform f plus Laplace transform g. In fact, if we have more functions, f plus g plus say h, then we also split into the sum of three Laplace transform. Furthermore, instead of addition, if we have subtraction, then we just change the sign here into minus. And then we also have Laplace transform of, say, constant, say k times f of x. Then we may take the constant k outside times the Laplace transform of f of x. So these two properties together is called the linearity. Now the next property would be extremely important in solving differential equations. It gives us the relation between Laplace transform of the derivative and Laplace transform of f. So you see that in above I use f of x, g of x, but here I just drop the independent variable x, and that is okay to do, just to make the notation simpler. So what is the relation? We will assume that both functions f and f prime are exponentially bounded, so the Laplace transform are defined. Again, this is just a technical theoretical condition. In practice, all of our functions will be exponentially bounded. But I need to write the condition here to make sure it's mathematically correct. So then, what is the Laplace transform of the derivative? I will explain a little bit and then write out the formula for you to see. Laplace transform of the derivative, by the definition, is the integral from 0 to infinity of f prime of x e to the minus sx dx. And so we write the limit a go to infinity, integral from 0 to a of f prime x e to the minus sx dx. For this integral, we see that we have the integral of f prime and then exponential. This is a good place to use integration by parts to get the following formula. Fx e to the minus sx x from 0 to a minus integral from 0 to a of fx times minus s e to the minus sx dx. This follows from integration by parts. Let me just write out what u and v is. Integration by parts that we have used is u is exponential e to the minus sx, and dv is f prime x dx. If you do this, then du is minus s e to the minus sx dx, and we integrate f prime, so we just get f. Using the formula u times v minus integral of v du will have the above. Now let's plug x equal to a in the first expression right here. We plug x equal to a and then subtract x equal to 0. And we get still limit a go to infinity. And when we plug x equal to a, we have f of a e to the minus s times a. We plug x equal to 0, we have f of 0 e to the 0, which is just 1. So we have f of 0. And let's simplify the integral here. We have two minus sign. Minus here become a plus, and s is a constant, we can take it out. Become plus s times the integral from 0 to a of f of x e to the minus sx. F of x e to the minus s of x dx. Now, with the assumption that f is exponentially bounded, the limit of the first quantity would be 0 for large values of s. So I will get 0 here. Then minus f0 plus s. And let's rewrite the integral. When a goes to infinity, we actually have integral from 0 to infinity of f of x e to the minus s times x dx. For I'll just write large values of s, meaning that s must be bigger than some value. Uh, the value depending on f, we don't have the explicit formula for f, so we just say large values of s. But what is this expression? Integral from 0 to infinity of f of x e to the minus s x dx. This is just the Laplace transform of f, right? So we have the formula. Let me rewrite this second term first. So we have s times Laplace transform of f minus f of 0. This is an important relation. Laplace transform of f prime is s times Laplace transform of f minus f0. Because of this formula, we may use Laplace transform to solve differential equation. We also need the relation between Laplace transform of second derivative as well and Laplace transform of f. So if we have second derivative, then using the formula for first derivative, we will get the following. I'm not going to show you that, but we may use the formula s squared times Laplace transform of f minus s times f0 minus f prime 0. We will use these two formulas and other formulas of Laplace transform to solve differential equation in the next topic. And this is the end of this topic today.